Hello, my name is Nathan Dunnigan, and this is my Physics 2212 Lab 1 on charged tape. To start with the introduction, I will be talking about the purpose of the lab, which was to use experimental and computational models to determine the electric force on a piece of charged Scotch tape, and then determine how much excess charge is on that piece of Scotch tape. For some previews of the results, the charged tape repulsed each other, meaning that the tape in question was a positive charge, which means it lost electrons, and the charge of the tape was 8.96 times 10 to the negative 9 coulombs, and then for every electrons lost, I found that there are 6.78 times 10 to the 6 atoms, and also the computational model was very similar to the experimental model, which will be talked about later on. To define the physics principles with more detail, we must discuss why we use these equations and what they mean. The first model was that tape is modeled as a point charge, and we assumed that each piece of tape had equal and distributed charge. We also used the Coulomb's law, the electric force, and Newton's second law. For Newton's second law, we used it to determine the electric force and gravitational force, given that acceleration equals 0. So then by finding the gravitational force, we could set it equal to the electric force. For Coulomb's law, we were able to calculate the charge on a piece of tape using the F equals K Q1 Q2 over a distance R squared formula. For some more assumptions and models, we assume that only gravitational force and electric force act on the piece of tape. Air resistance can be ignored, and both pieces of tape have the same electric field and charge. We also treated the tape as a point charge with evenly distributed charges as talked about earlier. For the experimental model, some initial conditions was that the system is tape B and the surroundings are tape A and everything else in the room. The setup was that two pieces were electrically neutral tape 0.2 meters long were used. The third piece of neutral tape was placed flat down on the desk as seen in the top right picture as the base tape. Tape B was stuck to the base tape on the desk and ripped off in order to create a charge on the tape. This piece was then held near several different objects to determine the charge of the tape, and it was then attached to two books with tape A held underneath it until tape B moved in the upwards Y direction, and that distance was measured, which is seen in the bottom right picture. Prior to the experiment, I tested the charged tape and then I ripped it off, and it did indeed attract to my hand. Then before placing tape B on the two books, I hung tape B around multiple different objects to see which objects the piece was attracted or repelled to. To answer the pre-questions, U tape B was attracted to a neutral notebook, U tape B was attracted to a negatively charged pen, proving that the tape is positive, and U tape B was repelled by another piece of tape during the experiment. The results show that U tape B is positively charged, meaning that it lost electrons during the experiment, and tape B moved when tape A was 0.0192 meters under tape B. Now here is my data collection for the experimental model, showing the length of my tape, mass of my tape, the distance I measured between the two pieces of tape, finding the gravitational force, and then finding the electric force, and then how I solved for Q once I figured out what F electric was. I used that bottom equation for the F for the magnitude of the electric force and was able to isolate Q to find the charge of the piece of tape. To continue the data collection, I was able to determine the electrons lost by the tape by dividing the charge of tape by the charge of electrons. Using the area of the tape and the area of the atom, I was able to determine the number of atoms on the tape by dividing the area of tape divided by the area of atoms. And I was finally able to determine the ratio of atoms per electron, and I concluded that for every electron lost, there are 6.78 times 10 to the 6 atoms. Now to go into the computational model, it starts with naming the constants that remain true in every problem, such as K, Q, G, the tape mass and area, and the distance measured from the experimental model. I also used a scale factor similar to Lab 0 to ensure that the particles were to scale, so I included that here. The following assumptions were also made to ignore air resistance, treat a long tape as though it was a point charge, and assume that each U-tape had the same amount of charge. I then was able to put in the data that I collected from my experimental model under my data section, and then I was able to create tape A and tape B as point charges, seen as the orange and blue particles. And then finally, I was able to use some initial values to find vector R and then create an arrow showing the electric force going upwards in the Y direction, seen by the red arrow, and the gravitational force going down, seen by the yellow arrow. And you can see that the magnitude of the charge of one piece of tape is very similar to my experimental model, as well as the deficiency of electrons and the number of atoms for every electron. Next, I'll discuss the similarities and differences, and like I said earlier, there are very similar results in both portions of the lab, very similar charges, and the charges on the tape are not likely to be the same, so that could have some discrepancies between the two models, and some sources of error could be rounding errors or other electrical forces acting in the room. To To answer the what-if question regarding electrons having a positive charge and protons having a negative charge, there would be no change. Opposites would still attract and like charges would still repel, and there would be a loss of protons instead of electrons in this case. Now to answer the why is it important to handle the charged tape as little as possible, it is because additional interactions with other objects could cause the tape to lose the true charge. And then finally, to conclude this experiment, assumptions must be made and stated to ensure accurate results of the experiment. Newton's second law is still very useful, and this proves that everyday objects can be modeled as point charges for simplicity reasons. And finally, it is important to use standard coding rules with glow script to ensure accurate conclusions.